Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section, we're going to continue talking about our inverse trig functions that we talked about in the last section. But in this section, we're going to move ahead more into the calculus and talk about the derivatives and the integrals of these inverse trig functions, or I should say the derivatives of these trig functions, okay? And the corresponding integrals that arise because of that, okay? So in the last section, we covered the basics of these inverse functions, why they exist, the ranges of the angles that they can return and things like this, okay? And in this section, we're going to define the derivative of every one of those inverse trig functions, and we will work some problems that talk about that. So rather than derive them all, I'm just going to put them up on the board sort of as fact, because you're going to just end up having to use them, and we're going to use them in our problem. So I'm going to focus more on how to use them rather than how to prove them. Your book is going to be there to show you why they arise and how to prove that they arise. I'm going to focus more on, okay, this is truth. How do you actually use them to solve problems on your test, okay? So the derivatives of the inverse trig functions are as follows, okay? The derivative of the inverse sine function is going to equal 1 over square root 1 minus x squared. Okay? The derivative with respect to x of the inverse cosine function is very similar. It's negative 1 over 1 minus x squared. Okay, now look at that symmetry. That's kind of nice. The derivative of the inverse sine, or the arcsine, is equal to this. The derivative of the inverse cosine is the same exact thing with a negative sign out front. So that's very, very nice. Okay, the derivative of the tangent, the inverse tangent function, okay, is equal to 1 over 1 plus x squared. Okay. And let's just go ahead and continue on, I think, over here to make best use of the board, okay? The derivative of the inverse cotangent of x is just going to equal negative 1 over 1 plus x squared. So notice it's the same thing. It's the exact same thing. The derivative of the inverse tangent is equal to this. The derivative of the inverse cotangent is equal to negative of the same thing. So that's kind of nice. You see some symmetry here that makes your life simpler. The derivative of the secant function, the inverse secant function, I should say, is going to equal 1 over x times the square root of x squared minus 1. And by now I think you see the pattern. The derivative of the cosecant function inverse, or the arccosecant function, is just going to be equal to negative 1 over x times the square root of x squared minus 1. So you see it's the same symmetry. Derivative of the secant, inverse secant gives you something. The derivative of the inverse cosecant gives you the same thing with a negative sign. Now, the reason these derivatives worked out so nice was precisely because of the range of angles that we picked, or the smart math guys picked, when they defined these inverse functions. Those definitions, those specific ranges that were chosen, lead to these very nice derivatives, and the fact that they're so similar and so symmetric. So that's why that was done, for those specific ranges, okay? So notice that for every inverse trig function that we've talked about, we have a corresponding derivative. So you put this in your bag of tricks with everything else. You know how to take derivative of, of sine and cosine and tangent. You know how to take the derivative of a polynomial. You know how to take the derivative of various other things we've talked about all through calculus. Now here is just another function. It's an inverse trig function, and you have another table of derivatives that the smart guys before us derived and invented and proved to be true. And these are they. Now, because we have defined the derivatives of all of these things, then by definition you already know what the integrals of some pretty complicated functions are, okay? So because you know that the derivative of the inverse sine function is equal to this, then by definition you know that if you ever see the integral of this thing, the integral of this thing, it is going to be equal to the arcsine function. So just to kind of put that down, that each of these leads to an integral, okay? So for example, now you know without a shadow of a doubt that the integral of 1 over the square root of 1 minus x squared dx is equal to, by definition, the inverse sine function, or the arcsine function, of x plus a constant, because it's an indefinite integral, and you always have to have that constant there, because when you take the derivative of this, here you take the derivative of this, you're going to get back this. By definition, you take the derivative of this constant, it's going to go to 0. So you always have to have that. So in the rest of this section, all we are going to do is work problems that have some derivatives and some integrals here, and we're going to just use what we've learned. So every one of these has a corresponding integral. Integral of this is this, integral of this is this, and so on all the way around the board. Okay, so the first problem is, find the derivative. So the first function is going to say, what if I'm giving you a function f of x, which is equal to the inverse tangent, or the arctangent, of x cubed, and I'm just telling you on the test, find the derivative, which would be df dx. How am I going to do that? Well, before this section of the class, you'd have no idea, but now you know that the derivative of the tangent, inverse tangent function is given to you here. The only difference is that inside of this, the argument here, it's not inverse tangent of x, it's inverse tangent of x cubed. So here you have to go back to the chain rule that you've studied in the previous DVD and your calculus, which just says that if you have the derivative of a complicated function, the complicated function of things that you know how to take the derivative of, you basically just keep taking the derivative all the way outside, going and multiplying times the terms of everything on the inside, and you'll see what I'm talking about here. So if we're going to take the derivative of the inverse tangent, you know that that's equal to this, but you know the argument is not x, it's x cubed. So the way you proceed is you take the derivative of this guy just as you would normally, 1 over 1 plus x squared, but the argument is not x, it's x cubed. So the way you write it is x cubed, and then you square that. Okay? So let me make sure you understand what's going on. You know what the derivative of inverse tangent of x is. You know that it's equal to this. But you don't have the inverse tangent of x. You have the inverse tangent of x cubed. So you take the derivative using the thing that you know. You use the argument that you had, but now you're not done yet. You have to multiply by the derivative of the inside to make it complete. Derivative of x cubed is 3x squared. So you multiply by that. So then df dx, is just going to be equal to 3x squared on the top over 1 plus x to the 6th power on the bottom, because x cubed and squared, 3 times 2 gives you 6. So it's 3x squared on the top, 1 plus x to the 6th power on the bottom. So when I say you take the derivative of bigger and going in smaller, you take the derivative of the whole inverse tangent function using the argument that you had, plugging that in, and then you multiply by the derivative of the argument and keep multiplying by those derivatives until you get down to nothing else, and that's how you do it. If you need practice with the chain rule and this philosophy and what this means, go back and get the DVD prior to this, and there's tons of examples on the chain rule, and this is just one application of the chain rule. Okay, let's say the next problem you have is somebody gave you function y is equal to the inverse sine of x squared. Inverse sine of x squared. And we asked you guys, let's go ahead and take the derivative of that, dy dx. Well, it's the same thing here. You see, you're trying to find the derivative of this function, and we know the derivative of the inverse sine function. That was given to us just a little bit before, and the derivative of the inverse sine is 1 over 1 minus x squared. But we're not given that. We're given a different argument. So the way you proceed is you say, okay, well, this is going to equal 1 over the square root of 1 minus x squared, but I'm going to use this argument, so it's going to be x squared squared. Okay? The whole thing's going to be squared. Okay, and then you're going to multiply by the derivative of the inside, which is 2x, to make it complete. That's the chain part of this thing going on. You take the derivative of the whole thing, given the argument that you have, and then you multiply by the derivative of that argument, and that completes the chain, and that makes the derivative legal. So you use the table, you're just plugging in the argument that you have, which was x squared, and then you have to square it because that's what the table said, and then you multiply by the derivative of the inside. So what you would have here is just 2x over the square root of 1 minus x to the 4th power, because 2 times 2 is 4. When you have exponents like that, you just multiply like that. And this is the answer. This is the derivative. Okay? Now, what if I had a function f of x is equal to the inverse tangent of x over a? Okay, a is just a number. It's a constant. It's just some number. I don't know what it is, but I know that it's a number. Okay, and I want to take the derivative of that. I would say df dx is going to be equal. Now I know what the derivative of the inverse tangent is. That was given over here. Derivative of the inverse tangent is 1 over 1 plus x squared, but I have a different argument here. My argument here is x over a. So I'm going to plug in x over a here, and I'm going to say it's 1 over 1 plus x over a squared. Okay, but then to make it legal, I got to complete the chain and multiply by the derivative of the inside. Now this is just a constant. 1 over a here is a constant that sits out in front of that x. So this is just 1 over a. Okay, because this would be like the derivative of 2x. What's the derivative of that? Well, it's just the number that's sitting out front. In this case, it's 1 over a times x. That's what's inside here. So the derivative of this is just 1 over a. Okay, so that's why you have that. Okay, now to simplify that, what's going to happen here is, all that you're going to have is, what's going to happen here is on the top you're going to have 1 over, this a is going to come out here and you're going to have a times 1 plus x squared over a squared. Because don't forget, this is 1 over a, so it's like 1 times 1 and then a times this whole denominator. So this a comes from here, and then the inside I just left alone here, 1 plus, and then you have to square the top and the bottom, a squared, x squared over a squared. Okay? And if I want to distribute this a in, it would be 1 over a plus x squared over a. Okay? Because a times 1 is a, and a times this stuff, the x squared is going to stay. One of these a's is going to cancel with one of these, giving me 1a right there. Okay, and then finally what I can do if I want to just make this thing just a little bit more tidy is, just for giggles here, I can multiply the top and the bottom by a, which is just multiplying by 1, and that's going to clean up some fractions. So on the top I'll have a, and on the bottom I'll have a squared plus x squared. A times a gives me a squared. A times this fraction here, a cancels with it, gives me the x squared. So this is just a bunch of simplification, really and truly. I mean, the answer was up here. It's just that you're beating the fractions into a little bit simpler shape. So in your book, you might see something closer to this. In fact, if you had something up here, you know, all of those answers are really right. It's just a matter of how far you take the simplification. Okay, now let's say the next problem you have is an integral. We're taking the integral from 1 to square root of 3. Those are my limits of integration. And the integrand is 6 over 1 plus x squared. Okay? And I'm integrating over dx, obviously. And I want to pull off this integral. Now, prior to this lesson, you probably wouldn't have a good idea how to tackle this because you want to use substitution. That's not going to really work because there's nothing on the top. If you chose x squared as u and tried to do some kind of substitution, you'd be left over with an x and you wouldn't really be able to cancel it with anything. So it's really a dead end. But if you look back over here, when you find something that's appropriate, it looks like this is pretty darn close. If you take the integral of this, you will get the inverse tangent function just like we talked about before. But we don't quite have that. We have a 6 out there, so how do we fix that? Well, this one's particularly easy because since 6 is just a constant, we can just take it and pull it outside the integral. 1 to square root of 3 of 1 over 1 plus x squared integrated over dx. Okay, and now we have the inside exactly the same as what we have over here, so we know that this is going to equal 6, okay, times the inverse tangent function of x, because that's exactly what this is equal to if you look over there, and you're evaluating this from 1 to square root of 3. 6 times the inverse tangent function, and I can just put little brackets around here if you want to make it clear. 6 times the inverse tangent function evaluated from 1 to square root of 3. So if you're going to continue to evaluate this, you'll have your 6, okay, and then inside the brackets you'll have inverse tangent function of square root of 3 minus inverse tangent function of 1. That's what we're doing. We're evaluating at the top point of the integral minus the bottom part of the integral. That's from your basic calculus when you do a definite integral like that. Now you see why it's so important. We spent so much time in the previous section about taking inverse tangents. Because if you have an integral like this, see, this integral has nothing to do with an inverse anything, But when you evaluate this integral, you end up getting an inverse tangent answer, and in order to evaluate, you have to know how to do that stuff. Otherwise, you're just going to be lost. So what I like to do, and I actually do this on my paper, I put little curly braces here and I say, okay, I'm going to evaluate that first. Okay? What this means is the tangent of some angle is equal to square root of 3. And we've done problems like this, you know, in the last section and on and on. Okay? And don't forget that for tangent only returns values from negative pi over 2 to pi over 2. Those are the range of values for the tangent function. You can't return a value outside of that. So whatever angle you pick, it has to be between negative pi over 2 and pi over 2. So tangent is equal to sine of theta over cosine of theta. And I literally write this down on my paper when I do it, and I have to find an angle that's going to do this. Now what if theta was equal to, in this case, pi over 3? Would that work? Okay, well, here's a unit circle over here for reference, okay? And pi over 3 is like 60 degrees, so that's kind of up here. So this is pi over 3, and let's go ahead and do it. Well, if we had the sine of pi over 3 over the cosine of pi over 3, okay? Sine over cosine, that's what we're trying to do. Let's find out if this angle actually works. Is this the right angle? Sine of pi over 3, which is up here, is going to give me a positive number because it's projected over there, and it's going to give me a positive square root of 3 over 2, and the bottom is going to give me the cosine of that. Cosine of that 60 is like 1/2. The 2 cancels with the 2, so I do have square root of 3. So what we have found is that pi over 3 is the right angle. Okay, to evaluate this guy right here. Pi over 3 is the right angle because when I put it in, I get square root of 3, and pi over 3 is in the proper range between negative pi over 2 and pi over 2. This is going to take some practice with you walking around the unit circle between here to find the right angle. But in the end, we know that the angle is pi over 3 for this guy. So what I'm going to do, remember, this angle does reduce to pi over 3. So I'm going to erase this, okay? I'm going to erase this, and I'm going to go ahead and write this down like this. This is pi over 3. That's all that this was doing down there, is what we found this. And then over here, inverse tangent of 1. Okay, well, what does that mean? That means that basically you have a tangent of some angle is going to give me 1, which is the sine of some angle over the cosine of some angle is going to give me 1. And I think you can convince yourself, because that's a pretty well-known thing, that the only angle that's really going to happen is going to be at pi over 4. Okay? Pi over 4 is between the proper range here. Sine of pi over 4 would give me square root of 2 over 2. Cosine of pi over 4 would give me square root of 2 over 2. Square root of 2 over 2 divided by square root of 2 over 2 is 1. So this is really the only place in that range that I can have that guy reduce to 1. So this is the proper angle. I'm going to have pi over 4 here. Pi over 4. So you can also use your calculator for things like this, but I mean, you're really supposed to be using the unit circle and doing this here to make sure you understand everything. So we've reduced this integral down to 6 times the difference of 2 fractions. There's no common denominator between these 2 fractions, so I'm going to make a common denominator by multiplying this by 4 over 4, and I'm going to multiply this by 3 over 3. And the reason I did that is because I want to make a common denominator of 12. Okay, so 4 over 4 and 3 over 3, they're both 1. So what I have here is 6 times 4 pi on the top and 12 on the bottom. And here I have 3 pi on the top and 12 on the bottom. 4 times 3 is 12. That's why I did that. So then inside here, I have 6 times 4 pi minus 3 pi is just pi over, denominator stays the same as 12. And so I think you can convince yourself that this is going to be 6 pi over 12, which is just simply equal to pi divided by 2. Okay, pi divided by 2. So this is a long-winded thing, but the answer is pi over 2. That's the answer to the integral. You started out with something like this, you didn't know how to do, but you remembered, oh, this is probably in that table of inverse trig functions. Let me go look over there. You pulled the 6 out. The integral of this is equal to the inverse tangent. So you put this here, you had to evaluate at the endpoints of your integral, and then you use the skills that we did from the previous section to actually evaluate this properly. And you got pi over 3 here, and pi over 4 here. You just found a common denominator and did the subtraction, and that was the answer. Okay, now let's do another problem. Let's say you were given the integral, indefinite integral this time, of x squared over the square root of 1 minus x to the 6th power dx. And you needed to do that integral on a test. The first thing you do is, try to do, since we're talking about inverse trig functions, is try to go off and look at that table and figure out if there is one. When you look over here, you're not going to find anything really similar. There's nothing with the square root of 1 minus x to the 6th power anywhere in here. And you get this kind of thing with experience, but look at what happens if I do the following. What if I do a simple substitution here? Okay? What if I say u is equal to x to the 3rd power? Okay? What if I say u is equal to x to the 3rd power? You'll see why I do that in a minute. Then I take the derivative du dx, as I'm doing a regular substitution here. It's 3x squared. Okay? So solving for dx, dx is equal to 1 over 3x squared du. Make sure you're convinced of this. Move the dx over here and then divide over here, so you have dx is equal to 1 over 3x squared du. The reason why I'm doing it is the following. I'm going to make this integral simpler. Integral of x squared over square root 1 minus u is equal to x cubed, so I can call this u squared. Okay? Because if I do u squared, that's x cubed squared gives me my x to the 6th power. So this integral is the same, okay? But it's in terms of dx, and now I'm going to plug in what I found for dx. So it's multiplied by 1 over 3x squared times du. Look at what I've done here. I was able to transform this integral, because this cancels with this, into an integral in terms of u only, and it's a simpler integral. That's the point. You want to make them simpler. So integral of 1 over, okay, 3 times the square root 1 minus u squared du. Okay, that's what I did there. That's what I did there. And then just even making it even simpler, the 1/3 that comes from here, 1/3 can come out, so it's 1 over square root 1 minus u squared du. Okay, so look, I've changed it. I've made it simpler. The reason I did that is because if you look at this, okay, there is one over here that looks like this, and it looks like the arcsine function. Okay, it looks like the arcsine function. So this is an exact one-for-one. Integral of 1 over root 1 minus x squared is the arcsine. This is the same thing. It's in terms of u, but it's the same exact thing. So this is going to equal 1/3 times the arcsine, or the inverse sine, of u, because this is in terms of u, okay, plus a constant, because this is an indefinite integral. You always have to add your constant, and then you just plug back in what you had for u, just like we always do for substitution. So it's the inverse sine of x cubed, because that's what u is equal to, plus a constant. This is what the integral is equal to. Okay, so we started with an integral here. We couldn't really find anything that matched up with it in the table to help us, but we noticed right away that we had an x squared and an x to the 6th power and an x squared here. So if we define u in terms of x cubed, and we take the derivative giving us 3x squared, solve for dx giving us 1 over 3x squared, then when we did our substitution and put, in terms of x to the 6th power, we put u squared, because u being x cubed squared gives us what we had using our substitution here. Then when we put dx in, which is what we found here, we had a cancellation, which is the whole point of doing a substitution. You want to get that cancellation in the numerator, okay? And then we pull out our 1/3, okay? We have 1 over 1 minus u squared on the inside, and this integral is exactly given in our table over here of inverse trig functions as the inverse sine of u. That is the integral of this, is the arcsine of u plus a constant, okay? And then at the end of the day, you just plug in what you used for u in the first place. So in this section of the class, we have talked about the inverse trig functions, but more specifically the derivatives of those inverse trig functions. And when you do that, when you define the derivative of something, you by definition have an integral right there that you've defined as well. So we've talked about those. We didn't derive them. We just put them down and said this is the truth, this is fact, and this is how you would take derivatives that involve inverse trig functions, and also some integrals that involve some functions of x and such, that you can beat them into the shape of some of these integrals that involve the inverse trig function. So you have to use the skills that we've done in the previous section in order to do well at those, but with practice and with just getting the hang of how to do those, I think you can tackle that.